Hi, my name is Becca Barbera. I'm a grade 11 student at Cathedral High School, and today we'll be discussing the diffusion mechanism of plutonium plus 3 ions in sedimentary repository conditions using ab initio molecular dynamics. Nuclear energy is a fundamental method of energy production. It is the second largest source of non-carbon power and produces approximately 60% of Ontario's electricity and 10% worldwide. The Nuclear Waste Management Organization, which is responsible for Canada's nuclear storage and management, has proposed a deep geological repository as a long-term dry storage site of used fuel. Within the repository, there is a multi-barrier system composed of both engineered and natural protection, specifically an MX80 bentonite clay buffer sealant surrounding the copper-coated used fuel containers, all of which are further protected by the geosphere. Both sedimentary and crystalline rock formations are being considered as potential host rocks. However, this experiment is conducted under the influence of 6.0 molar sodium calcium chloride type brine solution found in sedimentary rocks, as they are mainly located around the Canadian Shield, which, aside from being closer and thereby more directly applicable to my life, is the site where the majority of nuclear energy is produced in Canada. I chose to focus on the diffusion of plutonium through MX80 clay as it is the last barrier before the geosphere. The reason why this project focuses on plutonium, aside from its intriguing appearance in Back to the Future, is due to the lack of data pertaining to this element. Many societal and political hesitancies and contributions have made the availability of plutonium in Canadian laboratories very limited because of its association with nuclear weaponry, resulting in its substitution with analogues such as europium or americium in many experimental studies, which will undoubtedly lead to slight discrepancies. This experiment's research is not only intended to provide insight into the diffusion mechanism of plutonium through bentonite clay, but to also aid in determining the optimal host rock and supply further data to be considered upon when performing safety and performance assessments, which will ensure public protection and support zero-emission clean energy production. As this is a preliminary study, it is difficult to hypothesize any particular outcome. There are no previous diffusion experiments on plutonium that are available for reference, therefore, in order to form a hypothesis, data pertaining to chemical analogues was used. Experiments on americium reported diffusion rates of close to 0. Neptunium experiments reported values of approximately 6 times 10 to the negative 15 meters squared per second. As both elements share similar characteristics with plutonium, such as atomic radii, valency, and thermal conductivity, the hypothesized diffusion coefficient is within the range of those two elements. The first step in this experiment was modeling the MX80 clay. The main component of MX80 is montmorillonite, which is a clay mineral containing one octahedral sheet of alumina between two tetrahedral sheets of silica. Once the sheet structure was complete, one aluminum plus 3 ion was replaced by a magnesium 2 plus ion, as indicated by Lowenstein's rule, which forbids aluminum-oxygen-aluminum bond formations within aluminosilicate networks. The unit cell was then geometry optimized using the DMOL3 module in Material Studio and GGA PBE functional. This process is important as optimized structures often correspond to how a substance occurs in nature. Once optimized, proper charges were assigned to each atom, using the ClayFF force field data, which is a general force field used for the simulation of hydrated and multi-component mineral systems. This unit cell is then replicated to create a 1x2x1 supercell that will be used in production simulations. To create space for the water molecules that are representative of the moisture found beneath Earth's surface, the C lattice parameter was increased to 18.8 angstroms, which is the associated length of a 3-water layer system that has been proposed as the most likely hydration state in a deep geological repository. Using the absorption locator tool's function, 30 water molecules and 2 sodium plus ions were inserted into the model. The number of water models was based on the pre-established 5 molecules per water layer per unit cell, and were modeled using the single-point charge water model, and the 2 sodium ions were inserted to create an electroneutral environment, as montmorillonite is negatively charged due to isomorphic substitution of magnesium and aluminum. The adsorption calculation was performed using the ClayFF force field, the Ewald summation method for electrostatic potential, and van der Waals atom-based forces, as with all future simulations. In order to run this simulation at ground temperature, 3 dynamic simulations had to be run. The first at 100 Kelvin, the second at 200 Kelvin, and lastly at 298 Kelvin. This was done in order to prevent the molecules from experiencing a thermal shock, which would cause great energy deviation. Using Material Studio's Foresight tool, the task was performed with the MPT ensemble, where the amount of substance, pressure, and temperature are conserved. This allows for changes in volume where the simulation can better model real-life occurrences. The pressure was set at 1.0 times 10 to the negative 4 GPa, which is standard atmospheric pressure, and the Anderson thermostat was used, as it allows for the use of the NVT ensemble, where volume is constant as opposed to pressure, in future simulations. The Berenstain barostat was selected for pressure control with a decay rate of 5.0 picoseconds. Following the simulation, a final preparatory run was conducted using the NVT ensemble. This last process acts to fully stabilize the interlayer model. A water molecule was then substituted by a plutonium plus 3 ion, which had been previously geometry optimized using the DMOL3 GGA PBE functional, and the same 4-step process was repeated. Next, using absorption pool calculations, the 6.0 molar brine solution found within a sedimentary repository was added to the model. The simulated groundwater follows the SR270 PW composition proposed by the Nuclear Waste Management Organization regarding sedimentary rock formations. Using previous reports that used SR270 PW to measure sorption and diffusion values of other elements in laboratory experiments, the number and collection of ions was determined, and where one molecule represents 1 mole, 2 sodium cations, 3 chlorine anions, and 1 calcium plus 2 cation, along with 1 water molecule were added. The optimization process was implemented one last time. The interlayer model is now complete and ready to run the simulations. Each dynamics simulation was executed using the Foresight module, NVT ensemble, and Nose thermostat for a duration of 1 nanosecond. Each simulation was run at a now steady 298 Kelvin, which is why the Nose thermostat was chosen. A total of 8 simulations were completed. The mean square displacement, or MSD, of each individual simulation was calculated. Then an average MSD of all the simulations was determined. A linear regression was performed on the average MSD, which will be used to determine the diffusion coefficient. Linear regression analyses are used to determine how changes in the explanatory variable, time, are associated with changes in the dependent variable, mean square displacement. Using the Einstein relation, where diffusion is equal to the mean square displacement divided by the dimensionality of the system multiplied by time times 2, the diffusion coefficient of plutonium plus 3 in the specified conditions was calculated to be 1.72 times 10 to the negative 11 meters squared per second. The diffusion coefficient was evaluated in 2 dimensions, as motion perpendicular to the clay layers is bounded, equating to 0 and thereby not being considered. I decided upon this project as I feel that the results are applicable and important, not only for the present population, but also future generations. The choice in energy production methods is crucial, and many individuals are fearful of nuclear energy due to its association with warfare, which may lead to negative preconceptions regarding personal and environmental safety, alongside used fuel management and isolation. Information on radionuclide migration gives confidence to both scientists and the public alike regarding the benefits and security of nuclear energy through sufficient containment of radioactive waste. As previously mentioned, nuclear energy accounts for roughly 10% of the world's electricity production. If taken to higher proportions, significant improvements to the global environmental energy crisis are to be anticipated, as nuclear power is considered both clean and sustainable. The main difficulty that I encountered doing this project was lack of time, due to long simulation durations, a multi-step procedure, and limited access to computing power. As a result, for statistical analysis, more simulations may be needed. There are still a lot more steps that should be taken in order to have a complete knowledge of plutonium's diffusion coefficient within the Deep Geological Repository. Data on diffusion in crystalline rocks' saline conditions is definitely something to consider, as is how oxides within each rock formation will have influence. Thank you very much for your time, and I hope that you and your loved ones are well.